dear children, welcome to today's class. Today we are going to continue exercise 6.2. 12th question. 12th question, we need to prove which of the following functions are strictly decreasing on open interval 0, pi by 2. Okay, four sub questions are there. The first one is cos x. The derivative of this cos x is minus sin x. And the interval is 0, pi by 2. And we know that in this interval 0, pi by 2, sin x is positive, but here we have one negative symbol. So this is less than 0 and this derivative is less than 0, means this is decreasing function. The second one is cos 2x. F of x is equal to cos 2x. Then f dash of x, we will get it as minus 2 sin 2x. F dash of x, we will get it as minus 2 sin 2x. Sin 2x is positive, but we have minus 2. So in total, this is less than 0. So the function is strictly decreasing. And the third one is f of x is equal to cos 3x. F of x is equal to cos 3x. Then f dash of x is equal to minus 3 sin 3x we will have. Sin 3x is positive, but minus 3 we have. So this is less than 0. So it is strictly decreasing. Now one more is there. F of x is equal to tan x. And we know that the derivative of tan x is sec square x. Sec square x means sec x all square. And we know that the square of any number is always greater than 0. So in this interval, this function is strictly increasing. In this interval, the function tan x is strictly increasing. Okay, now I am going to do 14th question. 14th question. Find the least value of a such that the function f given by f of x is equal to x square plus ax plus 1 is strictly increasing on open interval 1, 2. Then f dash of x, we will get it as 2x plus a. And it is strictly increasing means this f dash of x is greater than 0. Strictly increasing means this f dash of x is greater than 0. That implies 2x plus a is greater than 0. 2x plus a is greater than 0. Or we can write 0 less than 2x plus a. We can write 0 less than 2x plus a. Now, we are considering this interval, open interval 1, 2. So, we can write 1 less than x less than 2. We can write 1 less than x less than 2. We can write. And I am going to make this 2x plus a. So, I am going to multiply this inequality throughout by 2. 2 less than 2x less than 4 we will get. Now add a, then we will have 2 plus a less than 2x plus a less than 4 plus a we will get. Now just look at these two. Here 0 less than 2 plus a, and here we got 2 plus a, 0 less than 2x plus a, and here we got 2 plus a less than 2x plus a. We will combine it, and that means we can equate this 2 plus a into 0, or we can write this 2 plus a is greater than 0. 2 plus a is greater than 0. Then we will get a greater than minus 2. We will get a greater than minus 2 we will get. That means the least value of a, that is minus 2. The least value of a, that is minus 2. Now the 15th question. 15th question. Let I be any interval disjoint from minus 1, 1. I be any interval disjoint from minus 1, 1. Prove that the function f given by f of x is equal to x plus 1 by x. F of x is equal to x plus 1 by x is strictly increasing on I. Okay, I, that is any interval which is disjoint from minus 1, 1. That means we can consider any interval except this minus 1, 1. We can consider any interval except this minus 1, 1. Or you can consider any interval, and if you are considering, let I be our interval, then the intersection of I and this interval, that should be empty. Okay, intersection of I and this interval, I intersection open interval minus 1, 1, that should be empty. Okay, there is no common element in I and thus interval. Okay, we will take f dash of x, that is the derivative of x is 1 and the derivative of 1 by x is minus 1 by x square. Thus we can write it as x square minus 1 divided by x square. X square minus 1 divided by x square we can write. Now just look at the denominator, that is square. The square of any number is always positive, no problem. And thus x square minus 1. Here we are considering the interval such that that interval intersection or open interval minus 1 comma 1 is equal to 5. So the x square minus 1, that is always positive. That is always positive we will get if our interval satisfies this condition. So we can conclude f dash of x is greater than 0. If this f dash of x is greater than 0, then the function f of x is strictly increasing on the interval I disjoint from open interval minus 1 comma 1. Now 16th question. 16th question. Prove that the function f given by f of x is equal to, prove that the function f given by f of x is equal to log of sin x. F of x is equal to log of sin x is strictly increasing on 0 pi by 2 and strictly decreasing on pi by 2 pi. Strictly decreasing on pi by 2 pi. Now f dash of x is equal to log of sin x, that is 1 by sin x into d by dx of sin x, that is equal to cos x by sin x, and it is equal to cos x by sin x, and it is equal to cot x. Okay, cot x. Now 0 pi by 2. 0 pi by 2, consider any value in that interval 0 pi by 2. Let pi by 4. Okay, we will consider x is equal to pi by 4. Then we know that this cot pi by 4, that is 1 and that is positive. So we can say that this is greater than 0. F dash of x is greater than 0 in the interval 0 pi by 2. Therefore that is strictly increasing. 0 pi by 2. So we can say that that is strictly increasing. Now if you took any point in the interval pi by 2 comma pi, if you took any point in the interval pi by 2 comma pi, then this f dash of x is equal to cot x, you will get negative value. So we can say that this function is strictly decreasing in the interval pi by 2 comma pi, strictly decreasing in the interval pi by 2 comma pi. Now 18th question. 18th question, that is f of x is equal to x cube minus 3x square plus 3x minus 100. Then we need to prove this function is increasing in capital R. F dash of x is equal to 2x square minus 6x plus 3. We will get 2x square minus 3x square minus 6x plus 3 we will get, and 3 is common, take it outside, then we will have x square minus 2x plus 1, and this is equal to 3 into, this is actually x minus 1 all square. X minus 1 all square is x square minus 2x plus 1. Now just look at this f dash of x. 3 is always positive, and here we have a square of a number. Square of any number is always positive, so we can say that this f dash of x is always positive. If it is greater than 0, then we can conclude that this f of x is an increasing function in capital R. F of x is an increasing function in capital R.